This is going to be the lecture over the problems out of the week 2, chapter 1 material. We're going to be going over here about 8 of these, and I'm going to have very similar problems like this located in the homework section. That way you can just kind of go through and fill these out, and you can see if you understand the concepts well. If you do, then great. If not, then provide you with a little more practice. So, and you can expect to see some of these same problems, or something with the numbers changed around a little bit, on the quiz for this week. So I just want you to be aware of that. All right, so what are we looking at here? Let's take a look at number 1. What is the average binding energy per nucleon of oxygen-16 that has an atomic mass of 15.99492 atomic mass units? Now, you may be a little confused as far as where some of these numbers have come from. If you will go to, let's see if I can find it here in the content. If you go down here, the exam 1 material, then we're looking at chapter 1 structure of matter, and then we're looking at what's underneath that. You will see here physics, constants, and qualities. If you click on that, let's see, it should bring up a number of constants that have been discovered and notated, measured, so on and so forth. And so this will have a number of the constants that we will be using throughout this particular course. So a nice little summary for our purposes, at least for this assignment. Let's see if we can find it. Here we go. We have particles here in table 1-5, and we have the masses that go along with that. And these are given in atomic mass units. So if we were to go back and we were to look here, we would find here a proton is 8 times 1.00727. Well, where did that come from? Well, that came from here. So I went and typed that into here. Now, why 8? Why do we have 8? How do we know that we have 8 protons? Well, if you go and you look up the constituent or component parts of atomic 16, what you find out is that you have 8 protons. You're also going to have 8 neutrons, and you're also going to have 8 electrons. So, given all of those structures here, we know how many there are for each, and we know how many atomic mass units each one of these weighs. So if we go through here and we do the multiplication, what do we find out? Well, let's see, 1.007277 times 8. Come up here with 8.058216. Clearing that out, 1.008665 times 8. So we have 8.06932. Technically, there would be a 0 there at the end. Finally, 0.000548 times 8. We get 0.00438 4. Now, if we take all of those values and we add them together, what do we come up with? We come up with 8.058216 plus 8.069320 plus 0.004384. So adding all of that up comes to 16.13192. That's how many AMUs that we have. Now, what does this mean, the average binding energy? What is binding energy? How does that, what sort of meaning does that have in this? I mean, all I've done up to this point is gone through and add together all of the component parts for the oxygen atom. And I've come up with a weight. What that value there in the question is telling you is that if you actually weigh the atom itself, you're going to come up with 15.99492 AMU. So what's the difference? And why do you come up with one value as opposed to the others? It's because when you put all of these constituent parts together, what happens is, in order to be able to hold that particular structure, a little bit of that mass becomes energy. And now the atom is held together. So the question is, what's the difference between adding together the component parts and then subtracting out what the actual atom weighs? What do you come up with? Well, if I take our value here and I subtract out 15.99492, then I come up with 0.137 AMU. That's the difference. So if I come over here and try to find out what the energy is, I mean, I've got the mass for what is the binding energy, but what is the actual energy component to that? I need that in order to be able, I need the mass in order to be able to compute what the energy is. So that's where I'm going to right now. So 0.137 AMU times 931 MeV. Well, where did that 931 MeV come from? Well, we're going to go back to this list here. One atomic mass unit is equal to 931.481. And I'll go ahead and throw that 0.481 in there too. So I'll go ahead and throw all of that in there together. So this is going to be the actual energy. Up to this point, we've computed the mass. Now we're going to actually find out how much energy is in that. So 0.137 times 931.481. So I got 127.612897. And that's actually more significant digits than we should have. We'll just call it there. And actually, technically, I should call it here because I've got 3 significant figures here. I've got 6 here. And that's what I would end up with. All right, so per nucleon, I've got 127. And if we're looking at it per nucleon, basically this stuff right here, we know that the binding energy there, but it's very, very small. If we lumped it all in and just considered it per nucleon, then if we take 127 and divide that by the number of nucleons that we have, then we end up with 7. 0.94 MeV per nucleon. Now, if you wanted to just add together, if you just wanted to be strict about it and just add together the protons and the neutrons and put that as the actual amount of energy per nucleon, just among nucleons themselves, then it would be a little bit less than that. But if you included all of that together and just said, what is it per nucleon, that's what you'd come up with. Next, let's take a look here at problem 2. So we're going to determine the energy required to move an electron from the K to the L shell, both in tungsten as well as hydrogen. So what I've done here is I've gone ahead and given you what the energy levels are for each shell. So for the K shell for tungsten, it's going to end up being 69.5 keV. For the L shell, it's going to end up being 12.1 keV. Hydrogen, the K shell is going to be 13.5. And for the L shell, it's 3.4. So what is the energy required? Well, let's take a look here. For tungsten. To move from the K shell out to the L shell, it would take 69.5 minus 12.1. And let me get rid of that there. It's not confusing anybody. KeV. So what does that equal to? So if we're looking for hydrogen, what does that end up being? 10.1 eV. So basically what you're doing is you're taking the difference here between these energy levels. So this is the energy required here in order to be able to transfer from the K shell to the L shell. So let's take a look here at number 3. So what are the atomic and the mass numbers of the oxygen isotope with 17 nucleons? In other words, oxygen 17. Now, if you remember from what we just discussed, the number of protons here is going to be 8. Because 8 protons is what defines the atom being oxygen. But what about the isotope with 17 nucleons? Well, we end up with 9 because we take the difference between the 17 total number of nucleons, and since we only have 2 types, protons and neutrons, if we know that oxygen has 8 protons in it, then we subtract that out from the 17, and we end up with 9. So let's move on here to number 4. So we're going to calculate the mass defect for the oxygen isotope mentioned in number 3, so oxygen 17. So the mass of the atom is 16.999133 AMU. So it's very much like what we were dealing with up here. Except all right. So this part here, which, just a second, don't need that going. Okay, so the number of protons here is going to be 8. That computation is going to be the exact same as what it was before. So what about the neutrons? Well, we got to change that, don't we? Because we're dealing with a different isotope, which means we have a different weight because we have a different combination of nucleons. So if I take 9 times 1.008665, come up with 9.07795. Now, are the electrons going to be the same? Well, we are assuming here that the isotope is going to be electrically neutral. So yes, we're going to say that the number of electrons is the same. So now the question becomes, what's the sum of all of that? If I take all of those and add them together, what do we come up with? So this is what we're going to have if we add all the constituent parts of that particular atom together. Now, if I take that number of AMUs and subtract out what it actually weighs, which is 16.999133. There we go. That's the mass defect. All right, so now we're going to look at calculating the binding energy that's mentioned there. So if we take this mass defect, and it's the same type of thing as what we computed up here in this problem. So if we take that and multiply it here by 931.481 MeV, we're going to come up with that. So whoops. Let's make sure I have that right. 931.481. Rounding gives you 132 MeV. Calculate the binding energy per nucleon for the oxygen isotope for O17. So if I take 132 MeV divided by the number of nucleons, which we said was 17. And that's 7.76 MeV per nucleon. All right, so now let's take a look here at problems 7 and 8. So what is the energy equivalent to the mass of an electron? Well, how do we convert mass to energy? It's Einstein's famous equation right there. So we know what the mass is. And the mass of an electron, at least in MeV or AMU, sorry, is this 0.000548. Take that and multiply it by the speed of light squared, which actually is this roughly equivalent to 3.8 times, 3 times 10 to the 8th meters per second. Quantity squared. Now, we know how many AMU that is. The question is, what other units are we going to need in order to be able to compute energy? Do we have anything here? Do we have a conversion here for AMU into, say, joules, or for that matter, how many MeV or KeV that might end up being? Okay, so what are we going to do here? We've already got the mass here, and we've got this. So how do we convert this into energy? We need energy units, right? Well, I suppose I could take this and convert this into kilograms. And then, figure kilograms, meters per second squared or whatnot, and put that into joules. Another way to look at that is using this conversion right here. One atomic mass unit is equal to 931.5 MeV divided by C squared. So basically what that means is 931.5 MeV divided by C squared, which technically is what this is right here. And we'll go ahead and make a note of that. So, and I got to be careful here because we still have to multiply that by 0.000548. Because technically, it's here, one atomic mass unit is equal to 931.5 MeV divided by C squared. So essentially I'm multiplying this by a conversion unit right here. What that does is cancels out the C squareds. I don't have to worry about that anymore. So I've got 0.000548 000548. The AMU cancels out here because technically this is a conversion unit. If I take both sides here of, whoops, if I take both sides here and divide it by 1 AMU, I get 1 is equal to 931.5 divided by the 1 AMU. So this basically means that the AMU portions of this cancel. Of course, the C squares cancel. So I'm left with this times 931.5 MeV. So let's see if I can write this out a little bit more clearly. Don't need to be quite so Byzantine about it. Let's see. Spell it out step by step here. So another way to write this is if I take 1 AMU divided here by both sides, I get 1 is equal to 931.5 C squared. So basically I can multiply anything by 1 and it still comes out to be the same thing. So that's effectively what I've done here. So I've taken that expression, multiplied it by 1, which is what I'm getting here. And then when that gets multiplied by the C squared, those cancels, the AMU units cancel, and so I'm left with this, which ends up equaling 931.5 times 0.000548. So 0.51, and technically that's 0 MeV. Now, how close is that to what we have for the measured values of it? If we actually look here in the constants sheet, what do we end up with? Well, I would have run across it by now. Those are more English units. Let's see. There we go. Electron mass 0.511004. So I'm a little off. And I think that has to do primarily with the rounding here of this. I think if I were to maybe take some better measurements here, I have some better precision here, I would come up with more 0.511, which is generally what is the accepted value. So finally, let's take a look here at the energy equivalent to the mass of a proton. So again, we're going to use MC squared. Now, I'm not even going to bother putting down what C is equal to because we're not going to use it. What we are going to use is the same information that we had there, except what we need are the number of AMUs in a proton. Now, we had that earlier. We had that earlier here in the problem, 1.007277 AMU. C squared. Again, we're going to multiply here by the conversion factor. Which is 931.5 MeV divided by C squared, which of course is going to be divided by 1. All of that is over 1 AMU. And then that gets multiplied by C squared. Because again, I'm introducing the conversion factor that I've got here. I'm just multiplying it by this so that I can get rid of the MUs, keep the MEV, and when I do that, I can get rid of the C-squareds as well. It's a mess, I know, but that is what we're doing. So I'm going to end up with 1.007277 times 931.5. So I get 1.007277, which is not what I just wrote up there. 1.007277 times 931.5. 938.3 MEV. How close do we get? Let's take a look here. So let's see what I have for electron. See if I've got it here for proton mass. Well, I have it here in other units. I don't have it. Let's check the top. Let's see. Proton rest mass 938.3. What do we come up with again? 938.3. There we are. Very good. So that's where it all comes from. Hope you got something out of that, and I will look forward to seeing you in the next lecture.